Our first task in understanding motion is to quantify how fast something is moving. We do this by dividing how far it goes by the time it takes. xi is the position initially of the particle. xf is its final position. Ti is when it's at this location. Tf is when it's at that location. And this gives the average velocity over that time. If an object is moving at constant speed, then this ratio is the same for any time interval. We introduce a little notation to make this easier to write, so we have less symbols to write. And we define the displacement, delta x, as xf minus xi. So this object here, delta x, is a single thing, but it's made of two symbols. The first one is the Greek letter delta, which is often used in science for change. And then x is, of course, position. Similarly, write delta t is equal to tf minus ti. Note that xf, xi, delta x all have signs. In higher dimensions, these will be vectors. When we make our coordinate system, we need to decide where the origin is and what direction is positive. This choice is arbitrary. xf and xi clearly change when I move my origin, but their difference doesn't. That falls out. But the sign will depend on what direction we choose. If I take 2 points, say xi is here, xf is there, and then delta x is the change, this is a case where xi, xx, and delta x are all positive. You're on the right hand, you're in the positive side of the origin, and you're moving in the positive direction. Here is a case where xf and xi are both negative, but delta x is still positive. And it corresponds to moving closer to the origin. So if you know the sign of xf and xi and the sign of delta x, you can tell whether you're moving towards the origin or away from it. It's pretty obvious, but we're going to be repeating the same argument with velocities and acceleration. And in that context, it will be a little less intuitive. But you can always fall back on just reasoning about position and displacement to understand how things work. One important thing here is that the x's and the t's have units. So if I measure position in meters and time in seconds, then velocity will have units of meters per second. In this course, I'm going to ask that whenever you do arithmetic with objects that have dimensions, you keep the dimensions throughout in the intermediate steps. So here's a really simple question I could give you. I tell you that some person walks from a position at 3 meters to a position at 10 meters in 10 seconds. What's her average velocity? And the way I would like to see that problem done is you write v is equal to delta x over delta t. And notice that in this intermediate step, I put units. And this is very helpful because in the end, you just, combine the units and you get the right thing at the end. It's really good when we get more complicated expressions because you can check to see whether your expressions are correct or not. I think a lot of students balk a little bit at the extra time of putting these units in here. And this is just one of those idiosyncrasies that I have, and I'm going to ask you to do this, and we're going to take a little bit off points in your when we're marking things if you leave them out. Now, velocity, like position, has a sign. If I am at a positive x position and I have a positive velocity, that means I'm moving farther away from the origin. If I'm at a negative x position and have a positive velocity, that means I'm moving towards the origin. Pretty intuitive. In higher dimensions, again, it will be a vector. Now, in the case of uniform motion, we call the absolute value of the velocity the speed. For non-uniform motion, it's a little more subtle. Imagine I sprint at 5 meters per second in one direction for a minute. Then imagine I turn around and sprint back at the same rate for the same time. I'm going to end up back where I started. So my displacement is 0, and hence my average velocity is 0. On the other hand, the intuitive thing to call your average speed is 5 meters per second, because at all times, that's how fast you're moving. I think that construction is pretty straightforward. Whenever we talk about average speed in this course, the interpretation should be obvious, but it's a fun thing to think about. Now, there's a very important graphical interpretation of velocity. If I have a position motion graph, and I take 2 points on this graph, we defined the average velocity as x2 minus x1 over t2 minus t1. Well, that's the same construction as the slope of the line that passes through those 2 points. We call this line that passes through 2 points on a curve the secant line. And so the slope of the secant line gives you the average velocity. If you move these points closer and closer together, you're talking about the average velocity on a shorter and shorter time, and that ends up giving you the instantaneous velocity. And this is the kind of notation we typically use for this. And so the notion is that delta x is changing as you change the interval. And as you make the interval shorter and shorter, you get the instantaneous velocity. And as I said, for uniform motion at constant speed, this ratio is independent of the time interval. So the instantaneous speed is just the same as, or instantaneous velocity is just the same as the velocity you'd get for any other interval. You should recognize from your calculus class that this is exactly the definition of the derivative, which is just the slope of the tangent line. Here's a little graphical demonstration. So again, the average velocity is the slope of the secant line, which I've drawn as this red line through these 2 points. And if I want the instantaneous velocity, I move these points closer and closer together, and that secant line gets closer and closer to the tangent line, and the slope of this tangent line is the instantaneous velocity. And this actually gives you a nice way of approximating the instantaneous velocity. If someone, for example, gave you data that could be plotted to make a graph like this, you can estimate the average velocity by taking 2 points that are close together, finding the average velocity during that time, And if those points are close enough together, that's essentially the instantaneous velocity. Actually, you can do even better than that. So if you look at this graph here, that when I move these points far away from each other, the secant line starts deviating from the tangent line. But if I symmetrically move the 2 points, as in this case, then the secant lines deviate much less from the tangent lines in terms of slope. So here's a nice picture that you see that as I move these 2 points symmetrically, more or less the slope of that secant line doesn't change and is a very good approximation to the slope for the tangent line. So if you have some numerical data and you want to approximate the velocity at some time, just take 2 roughly evenly spaced points around the time that you want to know the average velocity, and then take delta x over delta t.